Hi everybody, I'm Razvi, and in this video we will walk together through the DearQA TryHackMe room. That is Dear Quality Assurance. It is one of the latest room on TryHackMe as of the 9th of February 2022, and as you can see, it's an easy room that involves a bit of reverse engineering and exploit development, that is binary exploitation. I decided to record this video for two main reasons. First, because I think it might be useful for somebody out there learning binary exploitation to better understand some basic concepts when it comes to exploit development or binary exploitation, pruning, whatever you want to call it. And second, because I find this as a great opportunity for me to test out my setup. If the quality of both the audio and video turn out to be good, I will be considering creating more content in the near future. Without further ado, let's get down to business. Let's see what this room is all about. As you can see, we have a binary here provided by the author, which by the way is Nobita. And we should first analyze this binary before deploying the virtual machine. So I have already downloaded the binary, as you can see here. And usually when it comes to binary exploitation, the first thing I do when I'm facing a binary is, of course, checking out what kind of file it is. For that, I'm using the file command. And as you can see, it's an ELF, that is a Linux binary executable, 64-bit, which will be defining what registers we have to use. They will be 64 bits, that is 8 bytes long. And we can also see that it isn't stripped. It's not stripped. This will make our life easier when it comes to reverse engineering this binary. The next thing I usually do is checking what kind of strings are there in the binary, just to have a brief idea at a first glance of what the binary might be doing. Because remember that if we see a string in the binary, it doesn't mean it's actually a relevant string. We could see a name of a function that is being imported but never used, for example. In order to do so, normally people uses the strings command, but I don't like it. I don't quite like it, and I'm going to show you why. Strings by default analyzes strings with a single 7-bit byte encoding, which is also called ASCII. That's the behavior by default. And if you want to analyze or look for other encodings, you have to manually specify all the flags that you want to look for. What I prefer to use is Rabin2, which is part of Radare framework, that allows me to look for strings in the binary regardless of its encoding, of their encoding. I will show you the help page to see what we will be using, which is the -ZZZ flag that allows us to dump raw strings to standard output, which is our terminal. And by default, Rabin2 looks for every encoding, in contrast to strings where you have to manually specify it. So I will be using Rabin2-ZZZ, and our binary. Okay, first we can see the section where it finds the strings. You can see here, for example, in read-only data, in text, which is the code segment, etc. And we can also see the encoding it finds, for example, ASCII, UTF-8, and there is nothing else for me to show you. Now, at a first glance, we can see that we have in the read-only data bin bash string, which I presume will be called somewhere at some point in the code. We have the congratulations string, which is what we will be aiming for. And we can also see there are some other strings. Now that we have just a brief idea, a fast idea of what it is doing, let us execute it, of course. So we can see it prints the welcome dear quality assurance. I am sysadmin. I am new in development. What's your name? Let's see what it does. Okay, so we can see it prints hello and apparently it echoes the input I just provided. So let's see if it is vulnerable to a formatted string vulnerability, which it isn't. And let us test some large input to see if it crashes somehow. If we manage to crash the program, providing a very long input, it means that the program isn't performing bounds checking on the user provided input, and we could manage to corrupt some memory and maybe hijack the execution flow. As you can see, we managed to get a segmentation fault, which is actually very good because it implies that at some point, somewhere, the program tried to interpret our provided input and maybe jump to that specific address. You want to, or what I usually do is, I want to reverse engineer it. I want to see its assembly code and I want to inspect what's the behavior. In order to do so, you can use your debugger or decompiler of choice, whatever you prefer. And I like using Cutter because it allows me to have a pretty nice graph view. Before actually inspecting the code, you want to know what protections the binary was compiled with. In order to do so, you can use the dashboard overview menu in Cutter, but I don't know why the latest version, which is the one I'm using right now, seems to be bugged and it doesn't show me if the NX bit is present or the position independent code flag is also set. Now we have, of course, alternatives to get this information, which I'm going to show you now, but for now we can see there are no canaries, which implies that we can overflow some data structures like the stack and there will be no detection. Also, there is no relocation read-only, which is also a protection that is out of scope for this video. Now, how can we manage to see if there is NX bit or position independent code? One of the tools you can use is the almighty checksec, which comes installed by default with Kali Linux that I'm using right now. And as you can see, well, let me rearrange this a little bit. As you can see, there is no canary found, as we previously seen from Cutter, but we can also see the NX bit is disabled and there is no position independent code or position independent executable, which means that the addresses of the functions declared in the binary won't change between executions. Okay, now that we can see this binary is vulnerable to pretty much everything, what I usually do is inspecting what are the functions the binary is working with, or what functions are there present in the binary. Now we can see we have the main function and we have a pretty suspicious function right here, which is called vuln, which, as you can see, performs several puts, printing congratulations, you have entered in the secret function, flashes the buffer to the standard output, and then it calls execv, providing as a parameter /bin/bash string, which basically means that this function is calling a shell for us. Okay, so that's the function that we want to execute somehow in the remote machine, in the victim machine, so we have a shell. Now, the main function of this program, the program itself, as you would try to say, where the program starts, which, well, it doesn't start in the main. There are functions executed before main, but talking about that is out of the scope of this video. And in the main function, we can see it, just like before, performs several puts, which is welcome, DearQA, I am sysadmin, what's your name? And it uses the scanf function to retrieve the user input. Now, as you may already know, scanf is one of those functions which is considered to be vulnerable because it performs no bounds checking. That is, it doesn't matter how long or how big the buffer where you specify it to write is, because it performs no bounds checking on the user's input. So if you provide a 100 bytes long input, which will presumably be stored in a 10 bytes buffer, it will overflow it. And well, it calls scanf and then it echoes what we just provided. Just to sum this up, we can see that scanf is reading and storing input into RBP minus 20 in hexadecimal, and printf is reading just exactly the same thing. And that's basically where the vulnerability resides. That's how this binary can be exploited and abused. Since it calls scanf, which is a function that performs no bound checking on a user's input, we will be able to write from RBP minus 20 in hexadecimal whatever and how much data we want, which in turn allows us to perform a buffer overflow and corrupt several structures in memory and registers that will basically give us the ability to hijack this program's execution flow and make main return to our vulnerable function instead of where it's intended to return when it finishes. I will be drawing the stack and what is actually happening in memory, because I find this kind of drawings, diagrams, sketches, whatever you want to call them, pretty useful when learning things in general, and especially binary exploitation, because it allows you to better understand how things are arranged in memory and how the stack works. As you may already noticed, since our variable is referenced relative to RBP, which is the base pointer of the stack, we are exploiting this binary in the stack. Now, how is the stack being exploited with this kind of function? Let's say we have our stack here, and I like to draw this with the higher addresses on the top of the screen, and of course the lower addresses on the bottom. It grows from higher addresses to lower addresses. In fact, this is how the stack works every single time, but you may find people drawing the stack upside down with the lower addresses on the top of the screen. It doesn't matter as long as you understand how the stack behaves and how it grows. What does it mean that the stack grows from higher addresses to lower addresses? Well, it basically means that when we have one element in our stack and we perform a push operation, the next element will be stacked under it. That is at a lower address. This address right here is lower than this one, which I'm drawing in red. Now, what is happening with our binary? Whoops. Well, when it performs the scanf call, which we have right here, let me draw this in yellow, we can see that the data is being written at RBP minus 20. Let's say that RBP minus 20 is right here. This is RBP minus 20 in hexadecimal. As you may already know, when data is written in memory, it happens just the contrary of the behavior of the stack. That is, the data is being written from lower addresses towards higher ones. Let's say that we start to write our data in RBP minus 20 right here, and we start writing our data just in this let me print this in red because it's easier to see, in this fashion. That is, we are writing data from lower addresses towards higher ones. Now, since we are using, or rather the binary is using a vulnerable function that performs, once again, no bound checking, we are actually able to write as much data as we want. Now let's think about this for a moment. If we start writing at RBP minus 20 in hexadecimal, 20 bytes in hexadecimal higher than this address right here, we will find, of course, RBP. This is where our RBP lives. Now, what is there one address higher than RBP? Where there's always what we usually call the saved return address. That is the memory address where the main function will return when it finishes, when this read instruction will get executed. Now, as you can see, since we are writing from lower addresses to higher addresses, we are actually able to overwrite all these bytes right here. We also will be overwriting RBP, and here is our exploit time. We will overwrite the return address of main function. And where do we want to go? What do we want it to execute? What instruction? Well, of course, our vulnerable function. These are the very foundations of a binary exploitation, hijacking the execution flow of this program using a buffer overflow. We will anyways dig deeper in all these concepts in a future video. Now that the theory is clear, we know what we have to do, we know how to exploit this binary, what the vulnerability is, and where do we want to hijack the execution flow. Let's see how we can actually do it. In order to write the exploit, I always go for Python using PWN library, but of course you can use whatever you find more suitable to your needs or you find yourself more comfortable with. So I will be doing an exploit.py file right here, and I will be importing all the module from PWN. Now, of course, the first thing you always want to do is specify the binary you will be exploiting. You don't have to always specify the context, but I like to do so because it automatically sets several PWN configuration flags like the architecture of the binary, etc. Now let us take some notes over here, and we see that the write of scanf is performed from RBP -20, which of course allows us to create our payload. We will provide it with 20 in hexadecimal padding bytes, that is until we reach RBP. Okay, so once again, if we have our stack right here, and let's say that we are starting to write over here, that is RBP -20. Okay, we start writing here and we start writing in this address and we go upwards towards higher memory addresses. Let's say that we reach RBP right here. Sorry for that. That is RBP. Okay, this gives us a distance of 20 in hexadecimal bytes. Since we are working in a 64 bits architecture, each address is 8 bytes long. That means that the next thing, in order to reach saved RIP, we have to add 8 more bytes to this one. That is writing 8 bytes in the saved RBP memory cell. Once we write these 8 bytes, the next thing we will write will automatically overwrite the saved RIP. Okay, so let us proceed. Okay, I'm using A for the first padding, B for the second padding, and now what we have to specify here is the vuln function address. And how do we get that? Well, here is where PWN comes in to save the day. We can statically analyze the binary using PWN and get the function address that we need. How do we know this address won't change between executions? Because the binary is compiled without the position independent code or executable. Okay, we can say here no py, no canary. Now, in order to do so, I usually call it static, and we have to invoke the elf function from PWN providing binary. And how do we get this address? Well, very simple. PWN allows us to use the variable we just declared, accessing its symbols table, and simply looking for the address of the function we want, which is vuln. How do we know it's called vuln? Because we see in here in Cutter. Now, since we are working in a little endian environment, just remember that little endian stands for the lowest byte of a given number is being written in the lowest address, where in contrast with big endian, where the biggest byte of a given number is being written in the lowest address. That is, let's say, for example, we have this number, okay, which is 2 bytes long. For example, this is the lower byte of the number will be written in the lower address. And if we have here address 0 and address 1, AD will be written here and DE will be written here. And how do we convert our number, our address here? Well, of course, once again, PWN saves the day. It provides us with packing and unpacking functions, which we can specify with pack for 64 bits this given address, this given number. And it will automatically convert it to 64 to 8 bytes, little endian, and of course, filling the number with zeros whenever it's needed. Now we have our vulnerable address, and the only thing that's remaining here for us to do is interacting with the actual binary. In order to do so, we have to declare the process, which, as you can see, I'm not specifying the file that will be executed because I gave the program a context. Let me execute once again the binary, my input after name and colon. So I will receive until in the form of bytes, because this will be written as bytes, until name. Then I will send my payload, and then I will start an interactive session because I expect my shell to be popped up. Of course, I forgot to multiply it right here. And you have entered the secret function. As you can see, we reached our vuln function, and if I'm not mistaken, now I am able to execute commands as the Kali user, which is the one that's executing the exploit and the vulnerable binary right now. And I have a shell, of course. Now what we have to do is execute it in the victim machine, on the remote side of the binary. For us to do so, we have to first deploy the machine. We have to wait for it to give us an IP address. In the meantime, we have already analyzed the binary, and let us wait for it to deploy. Okay, we have our IP right here. I'm already connected to the TryHackMe's VPN, and let us modify our exploit to connect to the remote binary instead of the local one. When we have defined our process right here, we can use what PWN calls a remote connection that takes 2 parameters. First, the IP, and second, the port. I know the port is this one basically because it's being stated by the author right here of the room. And with this little change, let us execute the exploit and see if we are able. It works because we have the shell in the remote machine, but I don't know why, for some reason, the output is invisible to me. I don't know why. It has just the same colors as the terminal, apparently. Okay. One workaround, one bypass to this program is printing this payload, writing this payload rather to a file and echoing the content of this file to the netcat connection. So let me open a file. Let's call it my payload, for example. We will be writing bytes, file.write, and we want to write our payload. Okay. And let me comment these things because I don't need them. Now let me execute our exploit. Okay, you can see now my payload file is ready. Let me print it in hexadecimal. Now, in order to exploit the binary on the remote machine, we will have to cut, of course, the payload. We will have to execute another cut with no arguments, so we will be able to actually provide commands to the remote session, and we have to connect to this IP on port 5700. Let us see. It doesn't seem to work because, of course, I have to surround this one as a single command. Now, let us test it out. Congratulations, you entered secret function, and you can see now I am able to see the output of the commands I was executing before. We have our flag txt right here. Let us check this out. And what is the binary architecture? Well, you know, it's a 64 bits, sorry. And this will be the room for today. Okay. That was Dear Quality Assurance. As you have seen, a pretty easy exploitation room. I encourage people to create more binary exploitation rooms, more pwning rooms, and I hope you found this video useful. If you have something to say, leave a comment below, and I will see you in the next one. Until then, GG.